Alright, so we're talking about gradient descent, and this is the website that I was talking about in the last video. You can probably see it up here. So this website is really nice because it has some simulators on it. And of course it has this beautiful portrait of Augustin Louis Cauchy, which is always nice to see. Cauchy's French mathematician, of course, and he invented the method of gradient descent that we will be looking at today. Um, so um, our motivation is to try to minimize this function, and so we took a look to see how to do that. This is a little bit different approach where we come at it with a quadratic function, but actually this is the Taylor expansion, which you can see down here. They forgot the Hessian down here. And so this also lists the gradient descent algorithm in a nice way here. So the gradient descent, how does it go? We're trying to minimize f of x, and so we have some function and we have some file, right, that tells us how to compute the function and also how to compute the gradient, right, when we actually implement this. And so we have to give it an initial guess and some kind of step size, and in this case we're going to be using a constant step size. And so this is the repetition here, x of t plus 1 is equal to x of t minus our step size. So this right hand side here, right, is starting at your point and moving in the direction of the gradient. Good. And then you just keep repeating that over and over again. Now this is the reason why I wanted to go to this website, is because this is a nice example. The curves that you see here are the level curves of some function, and you see the optimum is right down here at the bottom. Now this is a nice trajectory here, but what you can do is down here off to the side, you can move this around a little bit and see what happens when you change your step size to different values. Right, so for example, if we had too big of a step size, right, it can go crazy and start going all over the place, even with a nice smooth, with a really nice, well-conditioned, I didn't want to use that word, but that's the word, a well-conditioned quadratic. And so the other piece of that is that you can actually get your alpha too small, in which case you're just doing a lot more work to get down to the actual minimum. Okay, and so here's an example of something that's not so well conditioned here. You can see the reason we would call it that is you can see that the level curves are all smashed together as you get closer and closer to the optimum. And so in this case, what happens when we move the step size too far? So we're still pretty good here. We're getting to the solution, but now what happens when we go a little bit too far? There it is. You're starting to see this zigzag pattern that is very common with with gradient descent. Gradient descent is well known for a zigzag pattern to get down to the minimum. Okay, and so you can kind of play around with that a little bit. So we don't want to path like that, right? We would want to try to find an alpha that is nice enough that that's a very good alpha there. Because if we go smaller, and we could go smaller, notice that we don't even reach the optimum within this number of iterations anymore. So it takes a lot of iterations just to get there. Good. And in the other case, we have a badly conditioned non-convex problem. And so again, woo! You can see what happens when you change your step size too much. You can go wild. You can go all over the place. Yeah, so this is really something that you really this would be a bad problem to have to solve numerically, right? Because it's all over the place. Yeah. So you can see what's happening, right? Is that the level curves are being smashed together, and they're also on a curve themselves. So they're being, yeah, there's a couple of curves going on there. Good. And so one last thing I wanted to talk about within gradient descent is there is a really nice algorithm that you can use to find a good step size, and that's called this backtracking line search procedure. And what you do, I don't know if you've had something with complex, or not complex, but convex functions before, then you might see this expression down here might be somewhat familiar. I have a feeling this is coming from a convex function. Um, yeah, we won't prove this result. This is a sufficient decrease condition here. And so you might recognize this, right? On the left-hand side, this is just f being evaluated along the path for a given step. And on this side, it almost looks that way, but you're stepping about halfway over, and then this is uh, not in the gradient, but it's the magnitude of the gradient squared. And so this is something fairly quick and easy to evaluate on the computer to see if the current step size is good or not. So if this inequality is verified, that's what this is saying. If this inequality is verified, the current step size is kept. Otherwise, you divide by 2, or any number bigger than 1. Yeah, 2 is a good one. You don't want to get too crazy there. Okay, and so I've implemented that in MATLAB as well. And so here's the algorithm with the backtracking line search. So with the initial guess, we'll start off with some step size bigger than 0, and then we're going to take an initial estimate. I kind of go back and forth about this. I think it is possible to increase the step size again once you've estimated it, but in general, you might as well just keep the step size decreasing while you're at it. I mean, it will take a little bit more work sometimes, but the problem with increasing it is it's hard to know what to increase it to. So there's that. Okay. Anyway, while you have this true flag here, we check our left-hand side and we see if it's less than or equal to this right-hand side. And if that is true, break out of the loop. Otherwise, we divide our adaptive step size by 2. And then we keep doing that until we get a step size that makes this inequality true. And so once this inequality is true, we break out of the loop and we just go and do our gradient descent. Okay, and then we get the next value of x of t, and then you get the step size and use gradient descent and just repeat over and over and over again. Good. So we're going to talk about some stopping criterion as well in our MATLAB code. But let's see if we can finish this up. So here's a nice, you'll see this in the MATLAB code. The backtracking line search strategy works pretty darn well for most nice functions. And most of the functions we're going to be using are fairly nice. So once you get into some of the thousands and thousands of parameters, then it starts to get a little trickier. But yeah, and even with this badly conditioned error function, you can still see that the backtracking line search actually works pretty well. And even with this really terrible problem where we have a curved surface here that we're trying to get to our optimum value over here, and all of our level curves are smashing together, we still are getting pretty good results. So that's very promising. Good. All right, so that's the gradient descent. Next we want to do stochastic gradient descent. Now, why would I want to change my gradient descent? The problem with the gradient descent in what we're going to be doing is the error function that we're going to be using. And so the error function is going to depend on data, and we're going to have huge numbers of data points. And so the data parameters, or the gradient, is going to have to be calculated by pushing all the data points through your function before you can compute the gradient. And so the question is, um, can you estimate the gradient without using all of the data? And that's where stochastic gradient comes in. So let's see. Oh, we have a picture. Herbert Robbins is an American mathematician and statistician, and together with Sutton Monroe invented the stochastic gradient method, also known as the Robbins-Monroe method. And it's kind of interesting that this was done back in the 50s, and it's really made a huge comeback lately with the neural networks. And so, yeah, so what we're trying to do here, you can see, is we're trying to minimize over some x where we have a large number of values to compute. Now this might be kind of confusing here because if you think about it, if we're doing a line search, where I shouldn't say line search, I should say linear regression, where our slope and our intercept are unknown, then what we're minimizing over is m and b, right? The slope and the intercept. So we're actually in R2. But if you have 50 data points, then that's what's being summed here from I equals 1 to n. And so this fi of x here would be an individual error value for a single data point. And so in that case, this fix is actually that ti t sub I minus mx sub I plus b squared. Do you remember that? We'll take a look at it in MATLAB as well. In fact, well, I don't want to go over there right now. Okay, so we'll see that. So the idea is that right now the error function depends on a huge number of sums. We have to sum a huge number of things together. And like I said, if we're using like a sum of squares error, then this n up here is actually the number of points that you have in your problem. Okay, and so this is the approximation right here. And what we're going to do is we're going to approximate the full sum by taking a single point and making that our approximation. So we're approximating the full gradient summed over the entire data set with the gradient computed over a single point. All right. Yeah. I'll put up the notes for this will be in your chapter there, so you can check that out to be more explicit about what that is. Okay, so in the stochastic gradient method, here it is. So really it looks exactly like gradient descent. So what's different is just right here. In the gradient, instead of summing over all data points, you're just choosing a single point. Okay, and we'll see what that looks like shortly. We're just going to use the constant step size, although you could take a step size that goes to 0, and so they recommend using something where the step size values would be infinite if you summed them up, but if you took the squares they would be less than infinity. So something like 1 over t would work, right? Because the sum of, or 1 over n you could say, because the sum of 1 over n as n goes from 1 to infinity. That's a divergent harmonic series, right? But if you take the square of those, 1 over n squared, that sum actually does converge. Okay, so this says that it doesn't go to 0 very fast, and this says that it goes to 0 fast enough if you square it. So that's kind of a tells you how fast it should go to 0. All right. So I didn't really want to do the least squares there because they didn't really explain that very well. But this is where I really wanted to go. And in fact, let's start with the good convergence here. And so this is what stochastic gradient descent looks like. Very different than gradient descent, right? It looks like you're going all over the place. But what's important here is that you're moving in the direction of the optimum. What's very interesting here is what happens around the optimum. So even if I drop the step size very, 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 very small, do you see still what's happening? We're not actually converging to the optimum. Oops. Okay, step size, we haven't quite gotten there. There we go. What ends up happening is you end up converging to what's called a noise ball, and when you're doing stochastic gradient descent. So you can really see that as you crank it up. Um, you're going to be approximating the minimum, but you're going to be bouncing around the minimum. You're not going to be actually going towards, or you will be going towards the minimum, but you don't converge to the minimum. You just bounce around the minimum. Okay, and so we can play around with it here. You can see this is where alpha is too big, right? Because you're just um, bouncing too far around. Yeah, things get crazy for that one. So you'd want to crank that down to try to get it to behave a little bit better. Yeah, but even here, you can see again that, yeah, it's going to be hard to control that. Of course, you might be saying, what in the world are you doing? Why would you want to have behavior like this? Well, and the answer is because it's a lot faster than gradient descent with a full sum. And by that I mean if you have, say, 100,000 data points, um, every time you would compute a gradient, you would have to have a sum of 100,000 things um, before you could figure out which direction you want to go. But in stochastic gradient descent, you only have one direction. So you're just taking one data point out and you're saying, this is the direction I want to go. And so it moves a lot faster. And so, yeah, we're going to see that in just a sec. We can add some momentum terms if we wanted to. We're not going to do that in our class right now, but you can play around with some of the simulators on this website. So that was a lot of fun. Let's take a look at the octave file here, and go to our editor. We'll go to housingprices.m. So what's the purpose of this? We have data that represents housing prices, and the first column is square footage. Second column is the price of the house. This is a fictional data set, but we want to find a function that predicts price based on the square footage. And so we're going to try to use a line of best fit on that. And so you see that we have, 10 data points? Okay, so the first thing, I wanted to do this example from start to finish because we haven't talked about pre-processing very much. You might notice here that the x's are scaled a lot different than the y's, and in both cases there's a lot of zeros involved, so it might be good to rescale your data. And so it's a pretty common practice to take the data, each of the data, mean subtract it, and divide by the standard deviation. So that means that the new data set that you're working with has mean 0 and unit standard deviation, and so that's kind of a nice thing to have. And so that's what the purpose of this is. I give you a plot of the original if you want to look at it. I should probably just comment that out. You can comment it back in or take away the percentage sign if you want to see that plot, but it looks the same as the plot down here, the scaled plot. Okay, and so our new data then has mean 0, standard deviation 1, and be sure and keep these parameters around. You may need them at some point. I ran into that problem once before, and yes, I remember it well. So down here I'm using X for the domain and T for the range. I'm using T because it's short for targets in this case, so think of that as X is our domain and T is our target. M and our B those are our unknown parameters that we're trying to find. And then maximum number of iterations, just to make sure we don't get into an infinite loop. Alpha is our step size, which we're just fixing to be 0.01 for now. And the tolerance is going to be 10 to the negative 6 power, and that's how close to zero the gradient should be before we stop. Okay, so that's just setting up some of the parameters. And if we go down here now, so this is our main loop. Notice that y equals mx plus b, that's our line, right? So the y is a vector now that's 10 units long, right? And it's saving what the actual output of the line is with the current m and b. And so think of that as model output. And so the error vector is t minus y. This is a vector in R10, right? Containing the error at each data point. And so what is the overall error function? That is the sum of the squares of these, right? So that's the sum of squared errors that we were talking about. And so this is the full error function right here. That's why I'm saving it, so we can plot it later. And now if I want to compute the gradient, we computed that in the notes. And so this is the this is computing the partial derivative of the error with respect to m, and then the temp2 is going to be partial of the error with respect to b. But this is a temporary, like a middle point of my computation, because this is an actual vector, right? Error vec is actually a vector in R10, and this is x is a vector in R10, so you're component-wise multiplying these two vectors in R10, right? And similarly, temp2 is also component-wise. Yeah, I could have written that better, but I wanted to make it look like the notes. This is another vector in R10, and so the actual partial derivative is the sum of these values times 2. The 2's, you could get rid of the 2 if you wanted to. You could put the 2 with the alpha, but just so it looks like the notes, will keep the 2 in there. So em in this case is the partial of e with respect to m, the partial of the error with respect to m, and e sub b is the partial of the error with respect to b. And so that is the gradient. The gradient is made up of em and eb. This is a vector in R2. And so now we just adjust the parameters using gradient descent, and that's it. Just start repeating yourself. Notice that I put in a stopping criterion. That is, if the gradient is very close to zero, we'll bail out of our loop. And then at the end, it's nice to be able to plot a picture of what we have. So let's go ahead and run this and see what we've got. That's housingprices.m. Alright, so you can see here what the gradient is doing. Yeah, as we proceed, we actually did end up bailing out. That was a surprise. Sometimes you don't. So we started with a gradient of 911, and we ended with a gradient of 0. And that was found in 48 steps. And here is the plot of the error function. And so you can see that there is an error. So our error does not go to 0, right? Our error goes to like 4 or something. And you can see why in the picture. There is error between the data and the line, and so we're not going to be able to get rid of that error. But now this is the line that reduces the error as much as it can. And by the way, that gives us a gradient of 0. Good. Now let's compare this answer to what happens if we use an adaptive step size. Okay, so in the command window, we'll type in housing. I do clear things out in the code here. So housing prices, adaptive step size. Oh, wasn't that the right? What did I call that again? I guess I could just run it. Housing price. Okay, I'll just run it here. Okay. What do you notice about the error? In fact, let's take a look at the output of our algorithm. Amazing! Solution found in 2 steps. Done. Okay, that's kind of an extreme example. Of course, linear algebra would find it in 1 step. So it's not too surprising that adaptive step size found it in one, but it is nice to see that that really does work. It can find your error fast or minimize your error very quickly. Good. And so you can see what we did here for the change in our function. And the change in the function just comes right in this one loop here. Um, Adjust the step size using backtracking line search. And you can see the exact computations are here that we were making or that were suggested on the website. And so LHS means left hand side of the equation, RHS means right hand side of the equation if you want to check that out. Good. And then the last one I wanted to look at real quick was the stochastic gradient descent. So that's housing prices SGD. Maybe I'll go ahead and just run it from here. And let's take a look at our error function in this case. Now this is interesting. You'll notice though that the error function is decreasing and it's getting down to our minimum. It's not a smooth landing though, right? And so if we take a look at our output, what do we see? Oh my goodness, what is this crap? I shouldn't say that. Yeah, stochastic gradient descent, the gradient is all over the place, right? Which kind of makes it um, kind of amazing, kind of miraculous, kind of a miracle that this error function does actually decrease and converge to the noise ball around the optimum. Because from this, just looking at the gradient, you would say, oh my gosh, this is a big mess. And so the gradient actually is not converging, but the error function is. And so that's, I guess that will be the end of the story for now. And I will, yeah, I will try to make this a little bit clearer in the notes. And I will see you later.